Bismillah ar-Rahman ar-Rahim. Let's just turn off the internet. Okay. So we need to solve this quiz problem. Use the following vapor pressure and solubility at 25 Celsius. Determine each pesticide Henry law constant. So he wants to find HLC, Henry law constant, or KH. And atmospheric over molarity, atmospheric per mole liter. Find the percentage by volume that each chemical is present in the air while in equilibrium. How much? What's the percentage of this chemical in air with a solution of the same volume of water, and express the result as unitless Ka water, Ka air water value. So you have the following chemical. Well, I'll choose this and you will do the rest. So I will do diazinon. So let's look at diazinon molar mass or molecular weight. It is 304 gram per mole. Vapor pressure 16 millipascal. Solubility milligram per liter. So I will try to change the pressure to atmospheric, because that's where we're gonna find it in. Remember, you need in atmospheric here. So I'll change the pressure, and I'll convert the vapor pressure from millipascal to atmospheric. So pressure, atmospheric, is equal to, what is the pressure? 16 and let's see, millipascal to pascal. Remember, 1 pascal is equal 1000 millipascal, and then milli with milli, you end up with pascal. And now if you want to convert pascal to atmospheric, you can see this in your notes or in the Google. So 1 atmospheric, which is our famous unit for pressure, is equivalent to 101,300 pascal. So you end up at the end with atmospheric, and that is, it will be equal to, so 16 over 3 over, this is a small number, 1.58, 10 to the minus 7 atmospheric. Good. So we've changed the pressure to atmospheric. Now we want to convert also the solubility from milligram per liter to molarity, because remember, he wanted in molarity here. This is molarity, mole per liter. So the solubility, C water sat, and molarity, what is, it's 40 milligram per liter, and let's convert milligram, because the molecular weight is in gram per mole, milligram to gram, and you know 1 gram is 1000 milligrams, so milligram cancelled with milligram. And what is, this is gram per liter, and how much it is gram per mole. You divide it by the molecular weight, 304 gram per mole. So gram with gram, and you will end up with 40 divided by 1000 divided by 304, and this would give you mole per liter, and this would be equal to the solubility in molarity, 1.32, 10 to the minus 4. Now the Henry law constant in this unit, atmospheric per molarity, and we knew that the Henry law constant Kh using the Henry law constant, using the approach vapor pressure and atmospheric over the solubility in molarity, mole per liter. So this is 1.58 10 to the minus 7 atmospheric over solubility. Solubility, did I forget? Here is molarity, atmospheric molarity, and this would give you 1.2 10 to the minus 3 atmospheric bare molarity. Okay, so this is it. And then he need to find out the percentage by volume that each chemical is present in air. We could use the same mass balance approach that we did in class. The mass balance approach that we want to calculate the fraction of each component in the air, of the air-water system. And that is as follows. So the fraction of the component, let's say the first, we're going to do the first component, fraction of the first component in air. It's equal the concentration of that component in air times the volume in air. The concentration of the component in air times volume, of course, over the total concentration of the component in water times the volume of water. Remember in one of the slides here, we divide by the, of course, using the dividing by the volume of the air and water, because the volume of air and water are equal. Volume of air equal volume of water. So when you cancel everything, it's all gone. So you'll have sea air. So this is based on this, is equal sea air over seawater. And now we're going to use the definition of Henry law constant. K, air, water, sea air over seawater, concentration of the component in the air over the concentration of the component in the water. Okay, so fraction of the air, when you divide by sea air, 1, sea air over sea air is 1, seawater over sea air, and that is almost the opposite of Henry law constant. So it's 1 over 1 plus 1 over K A W. You could rearrange this equation, K A W, here and there. It will be K A W, which is Henry law constant, over K A W plus 1. So this is the fraction of the component in air. Let's do the first compound. So one way to do it is have a small table. You could have the KH that you had before. Let's say compound. Diazine. We found KH before in atmospheric bare molarity 1.2 10 to the minus 3. That's KH. That's Henry law constant. And you need to find out later on. This is by dividing by RT to find that dimensionless Henry law constant. So you divide, you find Ka water by dividing Kh by RT. And the temperature here was given as 25 Celsius. So you change this to Kelvin and you put it here. And of course you should use the R constant, the constant we choose for the class. And this, I'll give you the answer here, 4.91 10 to the minus 5. Once you found this, you could find now the fraction of air. Just do it like this. 4.9 10 to the minus 5. 4.91 10 to the minus 5 plus 1. And that is the fraction, which is 5 10 to the minus 5. You can see that if this chemical is easily could easily be evaporated. Well, you will from this analysis you could determine that if this chemical can be easily go to the air. But from this analysis you can see that this will stay in the water. It will be hardly in air. If you look at the other chemical, heptachlor, let's say heptachlor, I'm not going to use KH, I'm not going to give you KW. I'll tell you the fraction of air here. The fraction of the air is 0.37. Almost 37% of this compound is in air. A lot. While look at the fraction of this compound in air, a little bit. Very, very small. Okay, so you should find this example, and this is example number 1 for quiz number 3.